this chapter, we will be using calculus as a tool in curve sketching. In this video, we'll be sketching the graph of x to the 1/3 multiplied by x minus 3.
All right, this time the question is f of x is equal to x to the 1/3 multiplied by x minus 3. All right, so here we go. First of all, let's take a look at the domain. And as with some of the previous ones we've looked at here, there's really no issue with this. This is a cube root. This is a linear function. There's no issue with either one of those, so the product of them has no issues either. So the domain here is going to be x is an element of the reals. Just in the interest of space here, I'm just going to keep going along the top here. Let's take a quick look at the intercepts. So for the y-intercept, we're going to make the x-coordinate equal to 0. And you'll see here this is going to be 0 to the 1/3 multiplied by 0 minus 3. And so what happens here is we are going to get an x-intercept here at, x-intercept. Did not mean that. I meant a y-intercept here at 0. Sorry, for a quick second there, I was about to find the x-intercept, and I don't know why I was thinking about that. Now the x-intercept, a little bit easier, we're going to set x, well not easier, it's solving an equation here, but anyway. We set this equation up here. The only way that this is going to equal 0 here is if x is either equal to 0 from that first factor here, or x is equal to 3. So we've got the two intercepts here at 0 and 3, and we've got the one y-intercept here at 0, so at the origin. So I knew that that was going to pop up here, that x is going to equal 0. Okay, let's take a quick look here at symmetry. If I plug in negative x, that will be negative x to the 1/3, and then negative x minus 3. The negative can be pulled out of that cube root, and I can factor the negative out of here, but that is going to change the function here. So this is eventually going to become positive. Oh, sorry, I should have taken the negative one out there. My mistake, you can't see that. So the negative one there. So this is going to leave us with positive x to the 1/3 multiplied by x plus 3. Because that is not exactly the same as the original, but it's also not the negative of the original, this is neither even nor odd. So it doesn't have any of the symmetry that you'd expect with either one of those scenarios there. Let's look for the asymptotes. And in this case, no asymptotes because it's not irrational. So that was easy. Now let's take a look at the intervals of increase and decrease, which means we got to take the derivative. So here we go. So the derivative of this, we're going to use the product rule, so it'll be 1/3 x to the negative 2/3 x minus 3 plus x to the 1/3, and then the derivative of that x minus 3 factor is just going to be 1. Great. So now I'm going to factor this. I'm going to take out the 1/3, and I'm going to take out the x to the negative 2/3. That is going to leave me with, in this first expression, just this x minus 3. But over here, this is going to leave me with positive, because I'm factoring out a 1/3. Remember, I'm going to factor out a 1/3 from both of these, and I do that because I always take out the denominator. 1 divided by 1/3 is actually going to be 3, and x to the 1/3 divided by x to the negative 2/3, you're gonna subtract the exponents there. That's actually going to get us x, 3x. So we get 1/3 x to the negative 2/3. This is going to end up being 4x minus 3. Wonderful. Okay, now let's take a quick look at this. Because remember, to find the critical numbers of the function, I got to look at where my first derivative is either 0 or undefined. Well, it's going to equal 0 when x is equal to 3/4, and it's going to be undefined when x is equal to 0, because remember, that negative 2/3 pushes that into the denominator. So it's going to be undefined there. So it's equal to 0 here, it's undefined here. Let's take a look at what that does to this function on the number line. So here's 0, here's 3/4. If we look at our two factors here, if I plug in a value for x that's negative, this negative 2/3 is going to end up being positive because of that square in the numerator. So it's going to be positive to the left of 0, but it's going to be positive everywhere. In fact, the only place where this is going to become 0 is at 0 itself. 4x minus 3, though, is going to become 0 at 4/3. It's going to be negative to the left, positive to the right here. So what we're going to get here is this thing is always going to be positive. This is going to be negative to the left of 3/4. So it's going to be negative, negative, and positive along this line here. Meaning that the first derivative is less than 0 on negative infinity to 0, union 0 to 3/4, which means the function is decreasing on the interval negative infinity to 0. However, I can't include the 0 because that is where this function is undefined. Oh, I'm sorry. The function is undefined. The derivative is undefined, but the function isn't. So I'm sorry. Yes, we can include that. Ooh, sorry. I was as soon as it was undefined there, I went to kind of a different place in my head here. But the original function is defined there, and so that's not a problem. So it's actually going to decrease right through the 0. And in fact, because it's going to decrease right through the 0, I can actually set it up. It's decreasing right up to that 3/4. The derivative is going to be greater than 0 from 3/4 out to infinity, which means this function is going to be increasing on that closed interval from 3/4 out to infinity. Now this opens up kind of an interesting spot here, because notice that the function is decreasing through the 0 and then changes at 3/4. So we know that this is going to be a min here, but that 0 does not qualify as a max or a min, so something kind of weird is going on right there. And actually what it looks like, because the derivative is undefined, but the original function is defined there, that looks like right there at the 0. This looks like it's going to be a vertical tangent. And we've seen that before. So for part 6 here, we know for sure that we're going to get a minimum, okay, at x is equal to 3/4. And, okay, I'm just going to plug this into my calculator. I feel that this is probably going to be a relatively odd looking number there. It's going to be 3/4 to the 1/3 multiplied by 3/4 minus 1. Yeah. So I'm getting this number that's about negative 0.2 when I round it to the nearest tenth. Like, I'm not going to be able to plot very accurately any kind of decimal. In fact, any kind of decimals that are significantly smaller than that, it won't make any difference to me. All right, 7. Whoops. Let's talk about concavity. So now we're going to take the second derivative, come back up to this thing right here. I will again use my product rule here. So I will take the derivative of that 1/3 x to the negative 2/3. So that is going to be negative 2/9 x to the negative 5/3. And notice something kind of interesting happens here. Up here in that first derivative, that exponent, the numerator was even. Now it's odd. Okay, so that's going to open up a possibility for us here. The negatives aren't going to be such a big deal. Multiplied by 4x minus 3, and then we'll take the derivative of that 4x minus 3, which will just be 4. So this will be plus 4/3 x to the negative 2/3. Okay, now I will factor out what's common. So I'm going to take out the common 2/9. And actually, I'll take out a negative 2/9 just so that the negative isn't giving me a problem later on. Okay, so this will be x to, then I'll take out the negative 5/3. That is going to leave me with 4x minus 3 in that first term, minus, I took out a 2/9 here, so that's going to be the same as multiplying this by 9/2. So the 3's will cancel, one of the 2's will cancel, so this will be 6. And then when I take negative 5/3 out of negative 2/3, that is actually going to be just 1 again. So just think about that. Negative 2/3 minus negative 5/3. It's basically going to be negative 2/3 plus 5/3, just x. So negative 2/9 x to the negative 5/3, and that's going to be negative, 4x minus 6x is going to be negative 2x minus 3. I will take out the negative from that. That'll cancel up here. So positive 2/9 x to the negative 5/3, 2x plus 3. All right, so now where does this go to 0, or where is it undefined? Well, because the first derivative was undefined at 0, this one's also going to be undefined at 0. So I know, okay, when x is equal to 0, this is going to be undefined. And then I know that this is going to go to 0 at negative 3/2. Okay, equals 0. So now let's just take a look at that number line there real quick. So this time we got negative 3/2 over here, 0 over here. This factor right here is going to be negative whenever x is negative. It's going to be positive whenever x is positive. 2x plus 3 will be negative to the left of negative 3/2 and positive to the right. So let's see here, they're both going to be negative over here, which is going to give us a positive value here. So it's going to be concave up here. Between negative 3/2 and 0, this factor here will be negative, but this one will be positive. So it'll be negative here, and then they're both going to be positive over here. So the second derivative is going to be positive from negative infinity up to negative 3/2, union 0 out to infinity, which means this is going to be concave up, negative infinity out to negative 3/2, inclusive, and then including the 0 out to infinity. Okay, because even though the second derivative isn't defined at 0, the original function is. Second derivative will be negative on that interval, negative 3/2 to 0, which means this will be concave down on that closed interval from negative 3/2 to 0. Notice that the concavity is always changing here, so what we've got is this point of inflection. Points of inflection at negative 3/2. Then I'm going to plug this in again into my calculator here, just to make this a little bit quicker to solve for. So that is going to be, negative 3/2, and then once again negative 3/2. Looks like I'm getting 2.9 when I plug that in. And then my other one here, again, when I plug 0 in, I get 0. All right, so let's take a quick look at what the graph would look like as a result. So once again, that origin is important. We saw over here, we've got this minimum at 3/4, negative 0.2. So 3/4, negative 0.2, put that over there somewhere. Then I've got this point of inflection at negative 3/2, 2.9. So negative 3/2, so over here, then 2.9 way up here. Actually, probably smarter to put this a little bit closer. Okay, so up here I'm going to identify what my first derivative is doing. So it's decreasing here, increasing here in this interval. Whoops, sorry, you can't see that. So the first derivative, break it up here and here. There's a break at 0, there's a break at that 3/4. The second derivative, how does that behave? Well, it changes at negative 3/2. It was positive, then it became negative, and then at 0 it changed again, it became positive. So what's happening here is the graph is decreasing and concave up, so it's going to look something like this. Okay, then it changes and it becomes concave Oops, sorry, it's concave up. As soon as I drew that, I thought, oh, that doesn't work. Okay, it's concave up. So here it changes. So it's concave up, doing something like this. Then it becomes concave down and decreasing. And we already knew that it was going to go vertical at 0. And then it's still decreasing, concave up. So it's going to come like this, but really quickly to our minimum. And then it's going to be concave up and increasing. And remember, we forgot that way over there was this x-intercept here at 3. So that is roughly what my graph is going to look like.